So, welcome back, everybody. I hope you enjoyed the food again. I just wanted to add again some information about the games. Maybe I was a bit fast this morning explaining. So the game with the card box, of course, you didn't have much time like this morning to do it, but maybe during the meal you can find your members, your group members. You can go listen, and you can also still listen on your own and then discuss with your group. Um, and also, I had some questions about the panel discussions. So this will be this afternoon, and at the end of the presentation, I will show you a slide with the different topics and explain how it works for the people that will be just as spectator, as audience. So don't worry, you will have all the information at the end of the presentations. And if you have to choose if you stay or not, we'll stay. Thank you. So to continue with the presentations, um, the next one will be kind of related with aeroacoustics. The next speaker will be Jules Colas, and he will maybe give you some possible applications of what we saw in the morning with Jean, for example, with acoustic simulation. So I let you enjoy his presentation. Thank you.
Okay, thank you. Hello, everyone. So I will be talking about the impact of the atmospherical condition on the propagation of wind farm noise. I'm doing my PhD at the LMFA, and my supervisor are Ariane Emanueli and Didier Dragna. To give some general context, since the Paris Agreement in 2017, there has been an objective to reach 32% of renewable energy in Europe in 2030. So in France, in 2019, wind farm noise represented 7% of the total electricity production. So it's approximately 25% of the renewable energy production just after the hydraulics power. And one of the main restraints of the development of this renewable energy is public acceptance due to visual and acoustic annoyances. So when it comes, so we will be mostly interested in noise annoyances, obviously. And so when it comes to wind farm noise, we are talking about really quite low levels. So when you are approximately, I don't know if this works. Yeah. So you can see on this graph, when you approximately 500 meters of a wind turbine, the noise level are comparable to ones of conversation talk. So it's quite low level, but when you're talking about noise annoyances, in these particular cases, you have to talk about two phenomena, which are amplitude modulation. So the fact that the noise of wind turbine is not a constant buzz, but you have some kind of woof due to the movement of the pail of the wind turbine, and also the fact that the noise is intermittent, which means that you don't have at the moment of a day or at the night or according to the weather, you don't have the same sound power level due to atmospherical condition and other things. So you kind of it's difficult to measure the impact of wind turbine noise. So when it comes to noise pollution, the fact that so the wind farm produce noise, this can cause the stop of the production at night, for example, because they make too much noise, and so you have to stop production. So it's not good for the efficiency of the wind farm. But it's also difficult to implant new wind farm because you have a public opinion, and you will have people that are against the implantation of wind farm because of noise pollution. And these two phenomena are going to be amplified because in the future, wind turbine will get bigger and bigger, and so the noise, yeah, maybe it's better. The noise they produce will also get louder and louder. So when it comes to the acoustical problem, we are looking at an aeroacoustic sound source, which are the blade of the wind turbine that are moving and that are producing sound, and producing sound, yeah. And this sound source, the sound propagate in the atmospheric boundary layer. So you have to add to the propagation meteorological effects. So for example, the wind. So usually you have a logarithmic profile, for example. And so you have to propagate sound in this medium. And also, for example, effects of the temperature and other atmospherical effects. But you have also the fact that the wind turbine itself modifies the flow as it encounters it. And so usually you have a wake just behind the wind turbine, so a deficit in velocity just after the wind turbine. And if you add to that ground effects, so for example, topography or ground absorption, you have a pretty complex problem to solve. And so if you want to do a prediction on the sound in the far field or on the sound produced by one wind turbine or several, you have to do a numerical simulation. So there has been already some work done on this topic. So first on not directly acoustic, but on aerodynamics. So mostly to improve the efficiency of wind farm, you have to kind of look for what flow is in the wind farm and what, for example, each position of wind turbine influence the flow. So this was done in the last year to improve efficiency in wind farm. Then when it comes to acoustic itself, so there has been some work to characterize and modelize a wind turbine sound source. So one of the last source model is an extended model, so taking into account, so using Amiet's theory to kind of model the airfall noise and so the blade noise. But you also have to take into account that there are several sources that are in movement. So those are already pretty complex source model. And when it comes to the propagation of noise in itself, so there has been already some work on the, like I said, on the impact of the wake, so the presence of the wake, so just the deficit of velocity just behind the wind turbine on the propagation. So what you can see, it's from an article from Barlas. So those are the sound power levels. So the wind turbine is at the position 0. And so this first case is without the presence of the wake. So there is no deficit in velocity just after the wind turbine. And this case is with the wake. And you see that this has a great impact on the sound power level. And at like one, yeah, at this distance, you have a burst in sound power level due to the deficit of velocity. So the wake has a great impact on the sound propagation. So here at LMFR, we started studying those different topics in 2020. So this pretty new, and this comes from a collaboration between our laboratory and the group Physics of Fluid, which is a group of the the University of Twente, which are doing large JDD simulation, so aerodynamic simulation on wind farm and wind turbines. So in this program, there is so my PhD thesis that started in this October, and also an ECL student project for 1 year on a particular type of inflow for the wind turbine. So now I will talk a little bit about what my topic is about. So it's to study the impact of the atmospherical condition, and so in particular wind velocity, for example, on the propagation of wind farm noise. So we can kind of divide this in 3 main objectives, I guess. So first, we want to study the difference between 2 numerical methods to simulate the propagation of noise. The first one is the method based on parabolic equation, and the second one is based on linearized Euler equations. And so we want to do this for several test cases and in presence of topography. And the second objective is to study properly a wind farm, so the noise propagation, so a multi-source problem, and by implementing a source model for the wind turbines and looking at different parameters. So for example, the relative position of each wind turbines, atmospherical condition, wind profile, also the impact of the source model on the results. And finally, we would like, because those are both 2D approach, and for inflow, and we would like to also look at some 3D study, and also to look at what unsteady flow, how unsteady flow influence the propagation. So now for the time left, I will just present what the thing that I've been doing. So just the comparison between parabolic equation and linearized equation, because I haven't started working on this yet. So just to give you some context on both methods, so really quickly, so when we are talking about linearized Euler equation, we're talking about equation that comes from the conservation of mass, momentum, and energy. And we're interested only in the small variations, so of the pressure and the velocity around mean quantities, so that are in blue here. So in the end, you get a set of two coupled equations on the pressure and on the velocity, and you have to take into account these mean quantities too. The parabolic equation on the other end is different because you start from the wave equation, so at the Helmholtz equation, so at a given frequency, and what you do is you're only looking in the wave propagating forwards, and you just want to solve the wave equation for this particular propagating wave. And here also you can take into account some mean quantities. So for example, a mean velocity profile in the wave number, for example, by using sound speed, an effective sound speed approach. So the benefits of both of this method, so this first one, we understand that it's more precise and more close to the reality, but it has a much heavier computational cost. And on this one, so we make several approximations, and we can't, for example, take into account backscattering because we are only propagating in one direction. But it's for parametric study, it's really better, and also for propagation over long distances because it has a much lower computational cost. So I'll just give you a result for both of these to compare. So we are propagating the sound so from a wind turbine in a mean flow with no topography, a really simple case. So the mean flow here, and you can see the wake, so the deficit of velocity just after the wind turbine. And so what we are doing with the linearized Euler equation is just propagating. So here a point source, though it's not a wind turbine. It's not really. It's not physical, it's just an impulsion that we propagate. So we have a time solution. And then from this time solution, we want to obtain something for the whole domain in frequency. So you can see here the wave propagating. And so we do a Fourier transform in the whole domain. And in the end, we can have for several frequency the sound pressure level in the whole domain. So this is what you get here. And so this is a plot of, so in decibel relatively to the free field solution. And so what you can see is, like we saw earlier, is the presence of the wake so it's different because the flow is not the same, but you create some kind of focalization of the sound power level at some distance. So it's kind of the same effect which we saw in the literature. So this is for a frequency of 100 hertz. And so if we can look also at, for example, the 200 hertz, so you can see that the interference figure is a bit different, but you still have some kind of focalization of the sound. And now we can do the simulation for the parabolic equation method, but in the same, exactly same mean flow. And so you obtain this. So this looks pretty much the same. So maybe it's better to look at the result at a given height. So it's here 25 meters. So we plot the same delta L for a given height for the both cases. And so we see that we have a pretty similar result. So the parabolic equation method in blue and the linearized Euler equation in red. So it's pretty similar. So we did other comparison, but I guess it was expected. So now what we would like to do is do the same type of comparison, but for a case with topography. So I show you two examples here of mean flow velocity with a hill. And so we expect here that the parabolic equation will have some error because there is no backscattering. So here you can't have some reflection and things like this. So we expect here to see more differences. And the two other things we want to do now is to use a different model than the point source, because for now I draw a wind turbine, but we are really just propagating an impulsion. And we also want to start to study a case with multiple wind turbine and see how they influence each other. Thank you for your attention.
Thank you, Jules. Simon, maybe you can turn on the light to see if we have questions. Yeah.
Hi, thank you for your presentation. I was wondering, you have shown us that the changes of the velocity field changes the propagation of sound. I was wondering if there are researches about production of sound due to the changes of the velocity on the environment. For instance, if there is an obstacle behind the um, the um, the system, will it create sounds?
Okay, thank you for the question. So here I didn't talk at all about the mechanism that produce the sound from the wind turbine. So I won't be really long, but this is like Jean explained. So we have blades that are moving, and so the sound comes from airflow noise and from impact noise. And so if you change the wind that is hitting the wind turbine, you will change also the sound produced. So for example, what we expect to see, for example, in wind farm, is that if there is a wind turbine just behind another, and so in its wake, it will produce a lower level, we expect, because there will be a lower velocity impacting the blade. But this is not, it's more complicated than that, and you can have other effects, but yeah, so there has been some study. I'm not sure there are particular study on the wind turbine and on wind farm. I'm quite sure there is not.
Okay, thank you.
Thank you, Jules. Yeah.
You say that you wanted to continue the work with another model than point source. Do you have an idea which model you want to use?
Yeah, so yeah, in fact we do, because we are working with so the guy I talk about here, so Benjamin Coté is we met him, and so we are going to implement his source model that he developed during his PhD and his research after. And we will work with him and implement his source model to propagate to use it in our study of the wind farm. So I don't know if you want detail on the model or not, but
Okay, thank you, Igor, for your question. Is there another one? Yeah, Jean?
I have a question on so now you are doing propagation of the noise. I don't know if you are planning to compare with some acoustic analogies like Fox Williams or something like that, that is not cheap at all. That is not that is cheap and easy to do.
no,
And
we didn't plan to, but I'm not sure what you're talking about when you're talking about acoustic analogy here, because here we do not solve the equation for the flow. Like we're using a mean flow, and we're just propagating inside. So I'm not sure this applies in this case.
and how do you predict the flow around the
So the
blades?
flow is a previous simulation. It's a large JDD simulation done by the group physics of fluid of Twente University. They are kind of specialized in large JDD simulation in the atmospherical boundary layer, and so they do a lot of research and a lot of simulation in wind farm. But like I said, it's more for like efficiency results and to see how wind turbine impacts each other. But so yeah, this is large JDD simulation. We use only the mean quantities. We could use, for example, using some different model to have
Yeah, yeah, you can, for example, take the pressure fluctuations on the blade and try to. In fact, I'm
yeah,
just trying to do some analogy with what we do in
yeah,
turbomachinery.
but
If if the same tools may be used
yeah,
or
but
not, I don't know.
if you look at the grid step for the simulation, it's around 10 meters. So you're not at all in the same
Yeah.
range to have some acoustics quantity.
Okay.
I'm, and here they don't. For example, the model for the wind turbine, usually it's just a disk that will, for example, it's a disk that will just stop the flow, and you have some pressure forces. So you don't really have acoustic quantities from those simulation.
Okay. Thank you.
Okay, yes, one more question.
Thank you for the presentation. I was wondering if you plan to take into account that the blades have a slightly different angle depending on the velocity that comes
Yes.
through the wind.
Yeah, so this is also in the source model, so we haven't really, we started to look at it yet, but I'm not really sure. So yeah, in the source model, the geometry of the wind turbine is taken into account, because the idea of the source model is that you use, so yeah, for each segment of the blade, you will compute a sound power level, and so this takes into account the geometry of the blade and also some, so the mean flow, just the velocity that is impacting. So I'm not sure you can take into account several angles in the velocity, but I'm not sure of this. But so yeah, you take into account the geometry of the wind turbine.
Thank you.
Okay, is there another question?